Now, ninth class students, just focus on this simulation. In this simulation, what do you find here? You find that we have a long thread or a string. Let me write here. This is string. Another thing that on the one end of the string means on the other end, we have attached a mouse. We have attached a mouse, and one end of the thread or the string we have fixed here with some rigid support. It is fixed. In the pendulum, this whole arrangement is called a pendulum, and the name given to this system is called simple pendulum. It's a pendulum. And now in this topic, what we are going to discuss, we are going to discuss or to find the time period of one oscillation. Listen carefully, ninth class students. Our aim is to find out the time period of one oscillation. Now, what do you mean by one oscillation, children? One oscillation means, please observe carefully, I will pull this string to a certain point with a small angle. Suppose I have pulled here till this point. Then I will release this pendulum. If I release this pendulum, then it will start oscillating back and forth about its main position. Now, once it is released from this point, then definitely it will go to the left side, means to the main position. After that, it will go to the left side. Then again, it will come back to this main position. And then finally, it will reach to the same point where it has been released. So that is called one oscillations. One oscillations means, children, like now see, one oscillation means now returning to the same point. That is one oscillation, and we need to find out the time period of one oscillation. Now, some of the students, they might say, sir, it's very easy to find the time period of one oscillation, that once we release from here, and then we can start switch stopwatch, and we can measure the time. Yes, definitely you are true. We can find the time period of one oscillation, but for the better accuracy, children, instead of finding the time period of one oscillations, we are going to find the time period of around 10 oscillations or maybe 20 oscillations. After that, after finding the time period of 20 oscillations, then we will find the time period of one oscillation. Now let me begin here. Now, one question for all of you children is, I want to begin in this on this slide, children. You can find out on the right side of my screen at the top portion, at the top side, you can find that there are still some options here in which I can change the length of the pendulum string. So initially, I want to start this experiment with a length of 0.50 meter. Now you can see, students, here the length is how much? It is 0.50 meter. And I also want to change the mass, and I want to begin this experiment or this simulation by taking a mass of 0.50 kilogram. Now this is 0.5. Let me hear 0.50 kilogram. Gravity is none, and friction is, let me make it, gravity is there. We are performing this experiment on the surface of Earth. Definitely that the gravity is there, and friction is none. No frictional force initially we are considering. On the left hand side, you can see that there is a stopwatch. And how we are going to do this experiment, children? As I told you, I will pull this pendulum to with a certain angle, with a small angle. Then I will release. When it start oscillating. After few oscillations, then I will switch on the stopwatch and I will start counting 10 oscillations. And after that, we will do the necessary condition. Now, the question that I want to ask all of you students, we are going to perform this experiment with a length of 0.50 meter. In the next case, we will increase this length. So is there any direct relation with the time period? Means, well, if we are going to increase the length, will the length make there is a change in the time period of the pendulum? Now, anyone students, please. Is length of the pendulum going to affect the time period of a simple pendulum? Charvi, Kim, any one of you, please. Any idea?
Yes.
Just say the question again.
The question is that is the length of the pendulum going to affect the time period of the
Yes.
simple pendulum? Yeah, you're saying yes,
Yeah.
it is going to change the time period. So let's see whether our this assumption is true or not. Now I will pull this pendulum. You can see here the angles. Generally, we suggest students to keep this angle very small, but I want to take this angle little bit large so that we can perform or we can measure the time efficiently. So this is 25. I have released the pendulum from the 25. Let me check one more time. Let me check it one more time. Exact 25. Yeah, this is 25. I will release. Now you can see this is starting oscillating about the mean position. After the few oscillations, children, now I'm going to keep my pointer on the stopwatch. I need to press the this stopwatch button when the pendulum is to the extreme right position. And let me press it now. Now one oscillation, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So now you can see, students, that the time for 10 oscillation is 9.54 seconds. Let me pause it. Let me pause it. 9.54 seconds. You please note down it in your notebook. Whenever I require this time, so I will ask you to please tell me. So the time period of 10 oscillation is 9.54. Let me do the same experiment. Let me repeat it one more time. For the 10 oscillations, I want to reset this time period here. Again, I want to take the same angle, 25. It's 25, yeah, it's 25. I have released after few oscillations. I need to press the stopwatch once the pendulum is to the right position, extreme right position, and then I need to start counting carefully. And yeah, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Here. Now it is 9.63. Every time when I do this calculation, when I measure the time period, every time I will find maybe a slight different answer. The reason is being that it depends on exactly at what time I press the stopwatch, I switch on the stopwatch, and at what time I pause the stopwatch, I stop the stopwatch. So it depends upon the presence of mind, how sharp or high actively or smartly I can press the stopwatch when the pendulum is exactly at the right hand side. So now in this way, children, that again, this experiment, actually, this activity is for your criteria B and C. It is basically for your lab report. So for your lab report, for your criteria C and D, you need to complete this activity in the lab, or maybe we will try to do this in online. And you have to perform the same thing. So that time period is 9.54 in the previous case, 53, it is now 9.63. So every time maybe you will get a certain time period. Now I'm going to increase the length. Let's see whether it is going to change this time period. And I want to take this 1 meter now, students. I'm keeping the mass same, the same gravity, the same friction. Nothing is going to change. Only we have changed the length. We will keep the same angle. All right, let me make this pendulum is pulled with an angle of 25 degree, and I'm going to release it. I need to release the reset the stopwatch also, and I am going to measure the time period of this pendulum in this time when the length of the string is 1 meter long. And so I'm going to switch on the stopwatch. Yeah, 1 oscillation, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah. So around 13 seconds, children. Around 13 seconds. In the previous case, when the length was ½ meter long, the time period was for 10 oscillation 9 seconds, around 9 seconds. But when we have increased the length and we make the length of 1 meter long, and at that time the time period of the pendulum has increased of 10 oscillations. Now students, here I want to tell you here how would you calculate the time period of one oscillation. So there is an equation or there is a formula. You may note down, children. Please note down. Time period, you need to calculate this time period of one oscillation. Time period of one oscillation or single oscillation. That is equal to total time. Total time means total time consumed in, if you are taking 10 oscillations, if you are taking 20 oscillations, more oscillation you will take, children, more accurate the result will be. Total time divided by number of oscillations. Number of oscillations. Whatever it is. So this is equal to total time. What is the total time here? Total time, let me take for the 1 meter long wire this time. This is suppose 13. Let me take 13 value, okay. And divided by number of oscillations are 10. So around 1.3 second is the time period of one oscillation. Similarly, when the length was, this is in the case of when L equal to 1 meter. Similarly, in case of when the length was ½ meter, it is 0.5 meter long. So in that case, the time period capital T is equal to the total time. I will take that around 9 seconds, students. 9 divided by 10 of number of oscillations are 10. So this is 0.9 seconds. So 0.9 seconds. Then you can see here the time period of one oscillation is different in both the cases when we increase the length of the pendulum. So you may note down, students, and let me pause the video. Now, students, from this observation, we can conclude that there is a direct relation between the time period and the length of a pendulum. There is a direct relation, means if we are increase the length of the pendulum, time period will also increase, means the pendulum will take longer time to complete one oscillation. Now, other thing, I want to go to the next experiment, and in the next experiment, children, again, I want to reduce the length to the ½ of meter, and this time, maybe I can keep it 1 meter. Suppose let me keep it 1 meter, but I want to change the mass. Initially, the mass is 0.50. Then definitely that for the 10 oscillation, the time period is for the one oscillation, the time period which we already calculated is 1.3 seconds. Now, if I increase the mass, if I, students, increase the mass, and by making it 1 kilogram. You can see here it is now 1 kilogram. The same pendulum is placed at the same position, means at the same laboratory, at the same room, under the same conditions, same environmental conditions, but we have now increased the mass of the pendulum. So my question is now, students, is this mass going to affect the time period of the pendulum? Will the time period increase, decrease, or it remains the same? Any students from grade 9? Jasmine, Tenzim,
I think it will increase.
it won't increase. Any other students?
I think it will increase.
Okay, it will increase. So let us check, students, here whether this time period will increase, decrease, or it remains the same. We can discuss after performing this experiment. Let me play. So again, the concept is, children, that you need to pull this pendulum to a certain angle, and this time let me keep the same angle, 25. You may the angle is 25, and I'm going to release this pendulum. Now I have to be very active to switch on the stopwatch exactly at the same time when the pendulum just crossed the right hand side position. And this is, yeah, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 around. So the time is 13 seconds again. And if you measure the time of one oscillation, children, then 13 divided by, I'm not taking the 0.42 value. I'm not taking the hundredth of seconds, this value, children. Just I am working on 13, a random result. 13 divided by 10, again, it is the same result, 1.3 second. Let me do it one more time, children. Let me do it one more time. 25 here, and reset the stopwatch, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's the same, around 13 again, children. That the difference between the decimal point, this always come because it depends the sharpness of mind, children, that how can I observe that the pendulum is exactly on the right position, and then I need to switch on the stopwatch. Exactly, not about the right hand side position. You can measure, you can start calculating from any position. You can start when the pendulum is reached at the mean position, then your one oscillation should be when the pendulum move to the left side, return to the main position, then to the right side, then again to the mid position. So you can also measure from that point also. It up to you, students. Now, when I have increased the mass, the time period is coming to the same. When the mass was 0.5 kilogram, time period of one oscillation was 1.3 second. When the mass has increased, double the mass, 1 kilogram, still it is the same time period, 1.3 seconds for one oscillation. Let me make it more larger mass, 1.5 kilogram, and let's check whether this time it is going to change. Again, the angle should be same, 25. Let me release, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Again 13 seconds, 13.45. So every time we are getting almost the same result, children, 1.3 seconds, 1.3 seconds, 1.3 seconds for one oscillations. So from this experiment, children, in the science, in the history, when the science was developing, at that time, the people, that the scientists, they were performing experiment. So they perform the experiment number of times, and after they are performing the experiment number of times, they finally gave a final conclusion. And the same thing here in the simple pendulum also, that this experiment was also performed by many times, and finally it is concluded that time period of a simple pendulum, let me write here children, and you also may note down in your notebook, time period of a simple pendulum. Basically, what if someone asks you what do you mean by simple pendulum? Simple pendulum is a long thread and a bob is attached. A bob means a mass is attached with the string. That is called a simple pendulum. And so time period of a simple pendulum is independent on mass of the oscillating object. Mass of the, let me write here, mass of the metal ball or oblique object, whatever you consider. It is independent. So mass is not going to affect the time period of a simple pendulum. We already proved here many years back, this already proved by the scientists, but we are repeating the same experiment here through this simulation. And even if you do this experiment physically in laboratory, then you will find the same kind of result, that mass time period is independent of the mass. Even you can increase that. In this simulation, there is no other option that to increase the mass. And if you move to the physics laboratory, then you can put different mass objects, 1 kilogram, 2 kilogram, 4 kilogram, 5 kilogram, and then you will also find the same type of observation. Even if you hold the wire, and if you start oscillating by yourself, means if you oscillate, you will find the same time period. If you ask your father to just hold this wire and swing, that in that case also the time period is going to be same, because it doesn't depend on the mass. Then the third thing which I want to check here, the gravity. As I told you students that we have performed this experiment, this simulation, whatever the result we have received here on the surface of Earth. Now I want to change the situation. Now we are going to moon, students. Now we are going to moon, and there are options that I can change. This is moon here, and I am keeping the same length. Let me keep it, the mass is 1.50 kilogram, but the gravity has changed. You know, students, as I hope that you are aware about from your previous class lessons, from the previous in grade 7 and grade 8, might be that the teacher you have told, or that the gravity is different on the surface of moon, and the gravity is different at the different planets, and on the moon that the value of gravity is 1/6 of the value of gravity which is on our planet, which is 9.8 meter per second square. So on the moon the gravity is less. So let's check whether gravity is affecting the time period of the pendulum or not. We have less time for this meeting, students. So let me repeat, do this experiment. With the same angle, I will keep the same angle 25, but remember I have changed the factor of gravity, and the rest of the things are constant. Even the angle is constant, length is constant, mass is same, that 1.5, friction is same, but the gravity is different. Let me release. And okay, now I will start when it will come to the right hand side. Yeah. One oscillation. Even you can see that the oscillation is small. Second, it is going slowly. It is oscillating slowly, that the time period is going to increase. Third, 4, 5, 6, 7, 8, 9, 9 now. And this is 10th. So the time period you can check here. It is 50 seconds for the 10 oscillation, and 50 divided by 10, that is around 5 seconds. So pendulum is taking around 5 seconds. It is taking last time. Gravity is less, time period is increasing, children. Gravity is less, time period is increasing. So it means I can conclude that there is some inverse proportional relation, inversely relation between time period and gravity. And I want to show you one more thing, children. And this is, we have one more option on the surface of Jupiter. On the surface of Jupiter, let me pause it first. On the surface of Jupiter, that the gravity is higher compared to the value of gravity on the surface of Earth. And it is about 2.5 times. It is certainly higher on the surface of Jupiter. And so if it is higher, let me check whether how this is going to affect the time period, children. Again, the same angle 25, release, and I want to measure 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So around 12, around 12. If you find the more, if you do the same experiment one more time, maybe around 11 and 12. So in this case, and in the previous case, when it was on the surface of Earth, that was around 13 point something. So let me check one more time whether it is exact the same 13 or 12. Let me repeat. And with the same angle 25, reset the watch, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, definitely it is different. Then the time period is now different as we are on the different surface, if we are on the different planet. So then finally, children, I want to give a very important equation you note down, as we have now 2 minutes left for this meeting. And you may note down that we have a very famous equation given by the scientist that time period of a simple pendulum is directly proportional to the length of the square root of the length, and time period is inversely proportional to the gravity, that acceleration due to gravity of that particular planet. And if I combine both these equations, students, so I will get a result that T is directly proportional to length divided by gravity under the root, under the square root. So this is a very famous equation of the simple pendulum to measure the time period of a pendulum. Or further, you can write this equation, T is equal to 2 pi into L upon G under the root. So this is a very famous result, children. And basically this experiment is not about the find the time period. You know, time period is easily we can find the time period with the help of Stover. But this experiment is to find the value of gravity of any particular planet. So if you perform the same experiment on the Jupiter, on the Pluto, on Saturn, on Mars, any planet, so you can calculate the value of gravity. That is a very important thing, that the gravity with the help of because the time period we can easily measure, length of the pendulum is easy to calculate. 2 pi, this factor is also a point of a research, that how this is 2 pi, but this when the scientists they performed the experiment, so they were satisfied that this value, it should be 2 pi, it cannot be 3 pi, it cannot be 1 pi, it cannot be 10 pi, but this should be 2 pi, and that is a constant value of pi multiplied by this number 2, and then you can calculate the value of gravity here. Now student, I want to pause this video as we have less time.